So far we had seen about some scheduling algorithms like first come first serve and the preemptive scheduling algorithms like the round robin. So in this particular video we will look at a class of algorithms for scheduling which are known as the priority based scheduling algorithms. So we will start this lecture with a motivating example. So let us relook at this particular example which we taken in the last video. So we had seen this round robin scheduling algorithm where we took 4 processes P1 to P4 and these processes arrived at different times 0, 2, 3 and 9 and they had different burst times like 7 cycles, 4, 2 and 1 cycles respectively. Now we will add a bit about the processes which are involved. Let us assume that P2 is a critical process while P1, P3 and P4 are less critical. So what is a critical process? So let us take an example of an operating system that runs in a microprocessor present in a car, and whenever the brakes are pressed, process P2 will execute and it will do several tasks related to braking of the car, while process P1, P3 and P4 may be less critical tasks. With respect to the car, again for instance process P1, P3 and P4 may be the music player. So one of the process may be the music player, while another one could be for instance controlling the AC or the heater and so on. So let us look at this Gantt chart again. We see that P2 arrives in the second cycle and it takes considerable amount of cycles to complete executing. The main reason for this is that this is a round robin scheduling scheme and other processes have a fair share of the CPU. So P2 first executes here and then there is P1 and P3 which executes, then P2 executes again and finally completes executing its burst at this particular time. Now you will see that there is an obvious problem with this particular scheme. Since P2 is a critical process such as controlling the braking of the car, it has taken a really long time for it to complete its execution, and this could lead to catastrophic accidents. So what one would have expected is something like this. Whenever a critical process such as P2 arrives in the ready queue, it should get a priority and it should be able to execute continuously irrespective of the fact that there are other processes with a lower priority present in the queue. So this is what we would like to have in a more realistic situation. So scheduling algorithms which take care of such priorities among processes are known as priority based scheduling algorithms, and this is what we are going to study in this particular video lecture. In a priority based scheduling algorithm, each process is assigned a priority number. A priority number is nothing but a number within a particular range. So this range is predefined by the operating system. For instance, the priority range is between 0 and 255. Therefore, every process that is executed would be assigned a priority number between 0 and 255. A number which is small, that is a priority number which is small, that is close to 0, would mean that the process is a high priority process or a high priority task. On the other hand, a large priority number would mean that the process has a low priority. So this is just a nomenclature which Linux follows. Other operating systems may have a different approach. So it would keep, for instance, a higher number indicating a high priority process, while a lower priority number indicating a low priority process. But for this lecture, we will go with the Linux nomenclature, where a small priority number means a high priority process and vice versa. Now, in a priority based scheduling algorithm, even though there may be several tasks present in the ready queue, the scheduling algorithm will pick the task with the highest priority. The advantage of the priority based scheduling algorithms is quite easy to see. Essentially, in an operating system which supports a priority based scheduling algorithm, tasks can be given relative importance, or processes could be given relative importance. High priority processes would get a higher priority to actually execute in the CPU compared to low priority processes. On the other hand, the main drawback of having a priority based scheduling algorithm is that it could lead to what is known as starvation. So, essentially a starved process is one which is not able to execute at all in the CPU, although it is in the ready queue for a long time. It is quite easy to see that starvation mainly occurs for low priority processes. So, let us see how starvation occurs with an example. So, we will take the same 4 processes P1 to P4 arriving at different times 0, 2, 3 and 9 and having different burst times 8, 4, 2 and 1. Also, let us assume that the priority of P1, P2 and P3 is higher than P4, or in other words P4 is the lowest priority process. We will also make this assumption that every 15 cycles this particular sequence repeats, that is after the 15th cycle of the processor P1 again arrives, P2 again arrives, P3 and similarly P4 arrives. So, this sequence of processes arriving into the ready state continues infinitely. So, what we see if you look at the Gantt chart is that depending on the priority P1, P2 and P3 are scheduled. However, the low priority task never gets scheduled within the 15 cycles. Additionally, since P1, P2, P3 and P4 arrive again into the ready queue after 15 cycles. So, again P1, P2 and P3 get scheduled while P4 never gets scheduled. So, as a result what we see is that this lowest priority process gets starved. Essentially, even though it is in the ready queue and just waiting for the CPU to be allocated to it, it never gets a chance to execute in the CPU because there are always higher priority processes which are arriving in the ready queue. So, let us see how priority based scheduling algorithms deal with starvation. So, essentially in operating systems which have a priority based scheduling algorithm, the scheduler would dynamically adjust the priority of a process to ensure that all processes would eventually execute in the CPU. What this means is that in our example, the priority of process P4 would gradually increase over a period of time until the point that it has a priority which is greater than or equal to the priority of the processes P1, P2 and P3. At that time, process P4 will get a chance to execute in the CPU. Thus, we see by elevating process P4 over time, the starvation that would otherwise have occurred since P4 was a low priority process is eliminated. So, there are several techniques that priority based scheduling algorithm could deal with starvation. So, we give one particular example here in which an operating system with a priority based scheduling algorithm could ensure that every process, even the low priority process, will eventually execute in the CPU. So, let us say in this particular operating system, when a process starts, it is given a base priority. Now, this base priority will differ from process to process. A high priority process will be given a high priority number, while a low priority process will be given a low priority number. Now, after every time slot or time slice, the priority of the process is increased by a fixed value. So, essentially all processes in the ready queue have their priority increased by a fixed value, except for the process that is currently being executed in the CPU. So, what you would see that over a period of time, all processes in the priority queue would gradually have their priority increased. Now, even a low priority process would have its priority increased up to the point that its priority is high enough, so that it is scheduled the CPU. So, after it is scheduled into the CPU and executes in the CPU, at the end of its time slice, its priority is reset back to its base priority. Thus, the process which starts off with the base priority of 250 will gradually have its priority increased. So, it is to a point that it begins to execute, and after it executes, its priority is reset to 250. Thus, starvation would be avoided. So, based on this, there are two types of priorities present for a process. There is the static priority, which is typically set at the start of execution. So, it can be set by the user who is starting that application, and by chance if the user does not set that particular priority, then a default value is taken. On the other hand, the second type of priority is known as the dynamic priority, where the scheduler can change the process priority during the execution in order to achieve some scheduling goals. For example, the scheduler could decide to decrease the priority of a process in order to give another process a chance to execute. Another example, as we have seen before, is to increase the priority of IO bound processes, since IO bound processes would typically require a faster response time. One disadvantage of having a range of numbers from which a process obtains its priority is the case when there are a large number of processes present in the system. In such a case, there may be several processes which are executing with exactly the same priority. For instance, let us say that our priority range is from 0 to 255, and there are maybe over 10,000 processes running in the system. In such a case, for each priority number, there may be several processes executing with that priority number. So, this is depicted in this particular figure, where we have 4 processes arriving at different time and having different burst times, but all of them have the same priority. So, in such a case, the scheduling would begin to behave like a non-priority based scheduling algorithm. For instance, it would begin to behave like a round robin scheduling algorithm. So, in order to handle this, what modern operating systems have is multi-level queues. That is, instead of assigning a single priority number to each process, processes are assigned a priority class. Now, there could be several priority classes within the operating system, and each of these priority classes could range from a high priority to a low priority. For instance, there could be a real time priority class, a system priority class, an interactive priority class, a batch priority class, and so on. All real time processes would be present in this priority class. Okay. So, each of these priority classes has a ready queue, and when a real time process is ready to execute, it gets added on to this particular ready queue. That is, it gets added on to the ready queue present in the real time class, priority class. Similarly, if an interactive process wants to execute and it is ready to execute, it gets added to this ready queue present in the interactive priority class. Now, at the end of a time slice, when the scheduler executes, the scheduler picks the highest priority class which has at least one ready process. So, for instance, the scheduler will scan through these priority classes starting from the most highest priority to the least priority, and it will select that particular priority class which has at least one process in the ready queue. Now, if there is exactly one process in the ready queue, then we do not have a problem. Now, that process is going to execute in the CPU. However, if we have multiple processes in the ready queue corresponding to the ready queue chosen by the scheduler, then a second scheduling algorithm would be used to pick or to choose from this set of processes. For instance, let us say the scheduler has decided to choose the interactive priority class because there were no other processes ready in the real time and the system priority classes. Further, let us assume that there are 4 processes present in the interactive class. Now, the second scheduling algorithm, such as a round robin or a FIFO scheduling algorithm, will then execute to determine which of these 4 processes will be assigned the CPU. Thus, in multi-level queues, there are 2 scheduling algorithms involved. The first is a priority based scheduling algorithm which chooses one of the priority classes, while the second is a non-priority based algorithm which chooses among the processes in that priority class. The second scheduling algorithm would typically be round robin, while for high priority processes the second scheduling algorithm is typically something like first come first serve and so on. Further, in schedulers that support multi-level queues, the scheduler could adjust the time slice based on the priority class that is picked. So, IO bound processes are typically assigned a higher priority class and a longer time slice. This ensures that the IO bound processes would be quickly serviced by the CPU as soon as possible. Also, the longer time slice will ensure that the burst of the IO bound process completes before the time slice completes. CPU bound processes on the other hand are assigned a lower priority class and given shorter time slices. The main drawback of having a multi-level scheduling queue based scheduling algorithm is that the class of the process must be assigned a priori. That is, we would require to know whether a process is a CPU bound process or an IO bound process. Now, this is not an easy thing to do. First, it is very difficult to identify whether a process is indeed an IO bound process or a CPU bound process. Second, a single process may act like an IO bound process at one time, but at another time it can act like a CPU bound process. That is, at one time it may have short CPU bursts and long bursts of idle time, while at other times it may have long CPU bursts and short IO bursts like a CPU bound process. Therefore, deciding a priori whether a particular process belongs to a IO bound process and it should be given a higher priority is difficult. So, one way to mitigate this particular limitation is to use schedulers which use multi-level feedback queues. In such schedulers, processes are dynamically moved between priority classes depending on its CPU IO activity. So, these particular schedulers work on this basic observation that CPU bound processes are likely to compute its entire time slice. This is because a CPU bound process will have a long burst of CPU, and therefore, it is quite likely that it would use up the entire time slice. On the other hand, IO bound processes have a very short CPU burst time, and therefore, it is not likely to complete its entire time slice. Okay. So, if you take this particular example, we can say that process 1 and 4 have completed their time slice. Therefore, these processes are likely to be CPU bound. On the other hand, process 2 has very short CPU bursts over here as well as here. Therefore, process 2 is likely to be an IO bound process rather than a CPU bound process. The basic idea of a multi-level feedback queue based scheduling algorithm is the following. All processes start with the highest priority or a base priority. Now, if the process finishes its time slice, that is, if the process executes until its time slice completes, then the assumption is made that process is a CPU bound process. So, it is moved to the next lower priority in the class. On the other hand, if the process does not complete its time slice, it is assumed that that process is an IO bound process, and therefore, it would either increase the priority class to a higher priority class or keep it on the same priority class. So, this, as you can see, is a dynamic way of changing priority classes of a process. However, the drawback is that we could still have starvation, and then techniques are to be implemented where starvation needs to be dealt with. Another drawback of this particular scheduling algorithm is that a malicious process could game the system and always remain in the high priority class. So, let us see how this works with an example. So, let us assume the malicious process knows the time slice of the system, that is, it knows whenever the time slice completes and it knows when a context switch occurs. So, let us say it has a loop such as this over here. So, essentially the malicious process will do some work for most of the time slice and then it will sleep till the end of the time slice. Now, as we know, when a process goes to sleep, it goes from the running state to the block state. Therefore, sleep will force a context switch to occur. Therefore, what is going to happen is that a new process will execute for the remaining of the time slice. Thus, for the entire time slice, for instance over here, process 4, which is a malicious process, would run for most of the time slice, and then just before the time slice completes, it goes to sleep, thus forcing an other process to execute. So, the other process 1 will now execute and just execute for a small duration. At the end of the time slice, the scheduler is going to see that process 1 has completed the time slice. So, it is going to assume that process 1 is a CPU bound process and move the process 1 to a priority class which is lower. On the other hand, process 4, which is blocked on a sleep, will remain in the high priority class. Thus, process 4 will be able to game the system. It will continue to execute from the high priority class, while another process such as process 1 will be moved on to a lower priority class. Thank you.